Alright guys, we are back. Apologize for the delay. Apparently I recorded this video once and then promptly deleted it. So I don't know what I did with this video, so I have to redo it. With that being said, due dates have been pushed back. The tests and everything are going to be due later in the week than just on the normal time. So I got to figure out exactly how far back I'm going to push them, but my fault. We do have the time to do it, and we'll kind of go from there. So continuing on with what we did. Last week I was informed that I had a mistake in my video. I corrected it. I have made comments in the section in the video to correct for that value. I incorrectly calculated one of the values. There is a comment now that's pinned that you should be able to see that correction. So like I said, with that, what I need to do is I need to update my notes. So when we were filling in this chart, we did the bridge circuit with our unfiltered. I calculated these values incorrectly. I used the right formulas. I just put the incorrect values in there. So to fix that real quick, what we should have ended up with was 26.138 volts DC with a 41.033 volt peak signal for our ripple, or peak to peak signal for our ripple, and that comes out to be 55.5% ripple. So that's what we should have seen between these full wave rectifiers. Between the full wave and the bridge, the only thing it does differently here is it pretty much doubles our voltage value that we get. Not quite, there's a little bit more loss, but nothing major. But either way, I wanted to make this correction. If you go through and you actually follow the formulas and put in the correct values, you're going to get these values. The numbers I had, I was inputting incorrect numbers, so I apologize for that. So we're going to continue on, and we're going to go through these different waveforms again through the filtered varieties. These ones are a little bit more difficult as far as that there's an extra step that we have to do. But like I said, they're not horrible. They're actually really easy, I think, and they're kind of fun. So anyway, so let's go ahead and shift over to today's tab. So the first thing that we're going to do is we're going to start off with our half wave, and it's going to be just filtered. So starting in as usual, we're going to have our input signal coming through a transformer. Then we go through that part, and then coming out we're going to have one diode because this is a half wave filtered power supply. Okay, so we have that value. This is going to come up. Our signal ground is right here. And then coming out of our output, we're going to go through a capacitor. And then we have our load in parallel with the capacitor. So again, we have, assuming 4-to-1 on our transformers, we're going to have the 120 volts RMS, 60 hertz. And so now this frequency is going to be a little bit more important. All right. So that's one of the things we'll have to keep in track of. So as we go through this, so remember, when we come into the beginning of our primary at point A, we have 169.7 volts peak. That hasn't changed from any of them. We go through our transformer, and we end up with 42.433 volts peak at 60 hertz. We go through the diode, and so then as we come out of the diode right here, we have 41.733 volts peak, because that's just what our full value of our secondary is, minus 1 voltage drop across the diode. So we come through, we're going to have capacitor 1, this is our load, and we're going to use a 22 microfarad capacitor, and we still have the same 1K ohm load. So now, basically what this is going to do is, at this point, our capacitor is going to fully charge almost instantly, because the voltage that comes through has this, comes straight down through the capacitor, comes back to ground, and goes right back into the circuit. So in here, we don't have any resistance. So our tau is pretty much just going to be the resistance of the wire, the resistance of the coil over here in the secondary of the transformer. So our tau time is going to be really, 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 really short. So a very, very small time that it takes to charge. So our capacitor is more or less going to charge instantly. Now, when the capacitor discharges, though, it's going to discharge through the resistor. And so when that happens, is we're going to lose a little bit of voltage, and then the signal is going to come back through from our waveform, and it's going to charge the capacitor back up. So our output is going to look like this. So we've got point A is right here on our primary, point B is, actually let's call this one point C, and point B is right here. So we have point A is our primary, point B is our total secondary, point C is after it's come through the diode, and in this case what we'll see here, and like I said, when we measure these, when we measure C, it's going to be just a voltage. I'm just splitting them up so we can see what happens. So we have this type of a signal coming through. So we have 42.433 volts peak, and this is at point C. Oh, sorry, that is point A. We have 41.733 volts peak at point C. So what's going to happen is because of this capacitor, it's going to, when the negative cycle, or when the positive cycle starts decreasing back down to 0 to where we get it clipped off, from this point, from our peak, it's going to start discharging. And then when it comes back around to this part, it's going to charge back up. And then it's going to discharge and you get it to a certain point, and then it's going to charge back up. So our output waveform is going to start looking like this. And so now we've gone from half of a sinusoidal wave to more or less a triangular wave. And so what we've done now is we have our Vmax and we have our Vmin. So what we have to do is we have to calculate, well, what is this voltage at a certain period of time? So this being our clue, we're trying to find the instantaneous voltage of this guy when it hits that time frame. Well, how do we figure that out? Well, if you go back and remember when we were talking about capacitors, we have this thing called tau. Remember, this is our RC time constant. So this tells us how long it takes. And it takes 5 tau for the cap to fully charge. And if our tau is really, really low, it's going to happen very, very fast. Okay, so that's kind of the idea that we're using here. So in this instance, now that we're starting to filter this guy, and basically all we're doing is we're storing the charge of the capacitor, the charge goes away, and then the capacitor starts to discharge, and then it's going to build back up once the cycle comes back around again. So what we've done here is now we've completely lowered what our min and our max voltage is. So our ripple voltage is just going to drop, drastically. So the first thing that we look at is what is the V minimum, okay? And we're going to use instantaneous voltage equation to solve for it. So the minimum voltage we have is going to be equal to the final voltage that our cap's trying to get to minus the VF minus VI. So again, we have V final minus V initial times e to the negative t over tau. So, well, how do we solve these values? What are they? So VF, this is where the capacitor is trying to get to. Okay, where the cap is trying to get to. The initial is our Vmax. Okay, this is where it starts. And then our T is the time that it takes for the waveform. Basically, what's the frequency of the waveform that we have? Frequency of waveform. And in this case, it's 60 hertz because we just have a half wave. And then our tau is going to be capacitor 1 and then any other resistance we have in the circuit. So in this case, it's just going to be RL, sorry. So now all we do is we just have to calculate what our new V minimum is. And then we can go through and we can solve all the rest of the equations just based on that. Okay? Give me just a second. All my notes got jumbled up. I thought I was ready to go. Apparently, I was not. There we go. There's the right page. Okay. Again, sorry about that. I apologize. All my papers got jumbled together and mixed up, and I blame my kids. Anyway, so now that we have those, we need to go ahead and solve for this value. Okay. So our t, in this instance, time, is going to be equal to 1 over our frequency. So 1 over 60 hertz. And that gives us 16.66 milliseconds. Our tau is 22 microfarads multiplied by 1 kiloohm. And that gives us 22 microseconds for our tau. So the idea here is it takes one, so remember, it takes 5 tau to fully charge or fully discharge. We have 1 tau is equal to 22 seconds, and then the total time we go before we push it back up to the maximum voltage, the maximum time it has to discharge, is 16.66 milliseconds. So we know that we're going to be less than a tau. So we know that it's not going to discharge more than about 63, 68% in that, remember that time frame. So remember the chart that we were looking at and the charge and discharge ratios of the capacitors. And so this is, kind of just a real quick estimation of where it's going to go. So, 65% of the value is what it's going to discharge down. It's going to lose. And then, so the ways we can control this, and the idea behind this is if we increase or decrease our tau, that's going to have an effect on how far down it charges. If we increase our tau, we make that number bigger. So we're going to say it's going to discharge a lot slower, it takes more time. Then we can get this to where it's not going to lose that much voltage, and therefore we're going to see a smaller ripple. So kind of think of that and keep that in your minds for the design phases. That's one of our knobs that we have that we can use to adjust this guy. So if we increase tau, we're going to increase the time, which is going to lower the amount of voltage that it actually discharges down to. And then the other option we have also is to change this time. But again, we only have 60 hertz or 120 hertz if we're using a full wave. So those ones are kind of set. We don't have much adjustment on the frequency, because if we plug it into the wall, we're not going to screw with the frequency at the power plant. It is what it is. It is what we have. So we just kind of move forward with that. Okay, so anyway, so when we plug all these values into our equation, we get our V minimum is equal to, so V final is it's trying to discharge down to 0 volts. Then we have V final again, and then the initial is where it started at, was at 41.733 times e to the negative 16.66 milli divided by 22 micro. Oh, I'm sorry. I goofed it again. This is 22 milli. Micro times kilo is milli. I should know that. Okay, so now we have this value. We're going to plug this into our calculator, and what this really comes down to is we have 41.733 times e to the negative 16.66 milli divided by 22 milli. So we got 0 minus 0 minus 41.733 times e to the negative 16.66 milli divided by 22 milli. And I didn't type that into that calculator. Get my other one that I can use better. And so what we end up with is our V minimum comes out to be 19.624 volts. So basically what that's saying is it's going to start out at the 41.7 volts. It's going to slowly discharge when the negative portion of the waveform has been cut off and there's no voltage, going back into the capacitor to keep it charged. It's going to discharge down to this 19.6 volts. And so now that it's done that, we have our max and our min. So now we can find our VDC by taking Vmax plus Vmin. We divide that by 2. So we have 41.733 plus the 19.624. Divide that by 2. Our VDC value that we have at this point is going to be 30.679 volts. So that's one of the ones we are looking for. Then we're going to find the ripple voltage. So basically, how much is it going to be changing from that value? So V ripple is equal to V max minus V min. And now remember that this ripple voltage we're measuring in peak to peak because it's the total delta. It's the total difference between where the min and the maximum is. How much fully is it changing? And so that's why we subtract these two because we just want the net change between these two. So we have the 41.733 minus the 19.624. Our V ripple is equal to 21.109 volts peak to peak. So, think of it this way, you cut that value in half in peak. So we're going to start at 30 volts or 30.7 volts, and we're going to be going up 10.5 volts. And then we're going to go down 10.5 volts on the negative cycle. So we'll actually be able to see what the max and the min is, but then we'll be riding on this 30.7 volt signal. So now that we have our ripple, we need to find the percentage because that's the value we care about because that's how good of a power supply we have. So the percent ripple, we take the V ripple in peak to peak, we divide that number by 2 root 3 because now, before we were doing 2 root 2 because we had a sine wave. But like I said before, what we've turned our sine wave into now is more of a triangle wave. And so to find the average of a triangle wave, we use the 2 root 3 versus 2 root 2. And so that's one of the big differences between these guys. So remember this value right here, this is when we have a non-sinusoidal wave. So like a triangle wave. Doesn't affect it a whole lot, but there is a little bit of a difference between it. And then we take, so coming back to here, we take our V ripple divided by 2 root 3, and then we divide that total by our VDC value. And then take that whole thing, multiply it by 100, and that gives us our percent. So we take the 21.109, we divide that by 2 root 3, and we divide that by our 30.679, multiply the entire quantity by 100, and we end up with 20.804%. So we can take these guys right now, and I'll go ahead and pull it back up on our other chart. So the chart, remember, is going to be in our, if you look at back in the notes, it's going to be back in the unfiltered. It's where we started all this guy off. So what I'm going to do, I'm going to pull that guy back up. I'm going to shift notes. So in our filtered half wave rectifier, we get a DC voltage of 30.679 volts with a 22.109 volt peak to peak. And that gives us our ripple percentage of 20.8%. So basically what that means is our DC value is going to fluctuate 20%. So you can see just by adding one capacitor to our circuit, we went from having, a 13 volt signal DC out to a 30 volt signal. And all we did was add in one component. We didn't change any of the other values. And we decreased our ripple voltage from 41 volts to 22 volts. So we went from 100%, 110% change in our DC value to a 20% value just by adding one simple capacitor. So, with that being said, that's definitely well worth the added cost of one extra component when we've taken our output error, is what you can call it, and we've reduced it 6 times. That's, quite a very effective business plan right there, honestly, for parts wise. But we've made this thing a lot more efficient just by throwing one simple capacitor in here. So now we're going to look at our full wave and the bridge rectifier, and we'll chart those as well. So I'll get back into ours for the filtered section. So the next section we want to look at is a full wave rectifier when we use just a simple filter. So again, we're going to have the same input. we have 120 volts at 60 hertz. We have our transformer. We have our center tap going to ground. We have our second set of diodes. And then coming off the output, just like before, we go into one capacitor that's 22 microfarads and our load, which is 1 kilo ohm. So again, we're going to go walk through everything, but it's going to be the exact same as what we did before as far as what our voltages are for the full waves. They're all going to follow the same pattern. So coming in here at point A at our primary, we have 169.7 volts peak. We come across into our secondary, and remember, our entire secondary is 42.433 volts peak. That's in the whole secondary. But because we're using the center tap, what it's going to do is we're going to get half of that value across each of these diodes. So we end up with a 21.217 volt peak on either side. And again, like before, when we take it off of the center tap, this bottom portion down here is actually going to be 180 degrees out of phase just because of the relationship between these coils. And because now we're taking it with the reference of our, to this reference point, which is no longer down here, it's in the middle. So with that reference point, it flips our voltage polarity because it flips the entire, our reference point is now moved and it's 180 degrees out of phase. And so that's why we get these full waves, because now we have a peak that comes up like this, or comes up like this, and then we're going to clip off this portion. And at the same time, we have another waveform that looks like this because it's 180 degrees out of phase. This portion is going to get clipped off, and so they're going to combine together to where we get this. Because if we don't, basically when we have these guys and we've shorted them together, all we've done is now we've completely inverted it. So our net, we're going to get this signal, we're going to get this signal. We're not going to clip anything off, and these are going to combine together and just give us a flat line. So because of the center tap, this is where we get this ability to use that. So we want this part clipped off, we want this part clipped off, and then this is what we end up with on our output. So with that coming through here, right before we get into the filtering, right after the diode, we lose 0.7 volts because there's only one diode we went through. And so we have 20.517 volts peak coming into this guy. And now the same thing is going to happen. So we're going to come up to this point, and as soon as we're fully charged, it's going to slowly discharge because now we're discharging through the load. Then it's going to charge back up, and it's just going to follow the curve with whatever it's sitting, and it's going to discharge. And then it's going to charge up and then discharge. And so we're going to get another sawtooth wave or a triangle wave coming out of this guy with this max and low difference from what we had before. So again, we're going to find this the exact same way. Our Vmax is equal to the 20.512 volts because that's where it's going to charge to. Our Vminimum is we want to know the instantaneous voltage of our capacitor while it's charging. So we're going to use that formula, Vf minus the quantity of Vf minus V initial times e to the negative t over tau. Now one thing to remember too is now our input signal was from here to here, and that's 60 hertz, but our output signal is now 120 hertz because we have two peaks in the same amount of time as it took us to get one peak. So our frequency is going to increase to the 120 hertz because we're using a full wave. That's one of the cool things about this is it gives us that extra bonus. Or not extra bonus, it gives us the extra frequency. So things are happening twice as fast for our capacitor. So they're going to not get charged up quite as, it's going to be faster. It's going to charge up faster and not have as much time to discharge. So we're going to take this, we're going to input the values. So we have 0 minus the quantity of 0 minus 20.512 times e to the negative t, and t is the inverse of the frequency. So it's 8.33 milliseconds. Our tau is R times C, which is again the 22 microfarads times the 1 kiloohm. And so that gives us 22 milliseconds. So come back to the formula, we're going to put the negative 8.33 milli. That's divided by the 22 milli. We plug that into our calculator, and when we're finished, we get a V minimum of 14.050 volts. So now that we have our max and our min, we can calculate everything else. So our VDC is equal to Vmax plus Vmin divided by 2. So we're finding the average, just like before. So we have 20.512 added to 14.050. Divide that by 2. The DC voltage we get is 17.281 volts. Okay, and now we need to find our ripple voltage so we can find the percent, find how good this power supply is. So our V ripple is equal to Vmax minus our V minimum. So we have 20.512 minus the 14.05, and our V ripple is equal to 6.467 volts in peak to peak, because it's the total difference between them all. And the percent ripple is equal to the voltage peak to peak, voltage ripple in peak to peak, divided by 2 root 3, because we have a square tooth, sawtooth wave now, instead of the sine, divided by our VDC. So this is 6.467 divided by 2 root 3. That's going to convert that to RMS, so we're comparing everything the same. And then we have 17.281. And don't forget to multiply it by 100 to put it in percent form. So our percent ripple comes out to be 10.804%. And that's the other number we need. So with using the exact same components, and all we did was went from a full wave unfiltered to a full wave filtered by adding in one capacitor, these are our values we get. Our VDC is 17.281 volts. Our V ripple is 10.804%, with the total amount of ripple that we had was 6.467 volts peak to peak. So now that I have those values, I'm going to go and put those back into our chart so we can compare and talk about them. So here we ended up with 17.281 volts DC. We had 6.467 volts of peak to peak of our ripple, which translates to 10.804%. Okay, so just comparing between our two full wave filter or full wave power supplies we have, going from filtered and unfiltered, we gained 4 volts in our DC. We lost 16 volts of ripple. And so, right there, we can see that just by adding the capacitor, it has a huge effect on what the circuit does. It makes them so much more efficient just with one simple little capacitor. And like I said, we went from 55% of our ripple down to 10. So we decreased it by 5 just by adding in one simple component. Okay, so let's move on to the last one. And the last one is going to be our bridge circuit, and we're going to filter that guy. So again, we have the same setup as before. Only now we're going to come through our bridge. I can draw that one a little better. Okay, so our bridge looks like that. Our ground comes off over here, and then at this point, we go to our capacitor to ground, and then we go to our load. So 1K, and our capacitor is at 22 microfarads. So again, going through to figure out what our voltages are, we have 120 volts at 60 hertz. At our primary, we have 169.7 volts peak, 60 hertz. Coming through the secondary, it cuts it down to 42.433 volts peak at 60 hertz. We run it through our full wave rectifier, and so we're going to lose 1.4 volts across the whole thing. And we end up with, so coming out of our rectifier, we have a 41.033 volts peak signal at 120 hertz. Because just like the other one, we took it through and ran it and took the inverses, the two 180 degree out of phase, and we end up with the two peaks coming out of this guy. And you can actually measure that. You plug it in there, you'll see that. So then the last part that we have now is we need to figure out what our minimum voltages are, so we can calculate how far down does the capacitor discharge in this scenario. So our max voltage is the 41.033. It's trying to discharge down to 0. So we use our instantaneous voltage equation, and we go 0 minus 41.033 times e to the negative t over tau. So our t is the 8.33 milli, and our tau is still the same at 22 milliseconds. So that's one of the nice things without this is we're not changing any of the other components, we're just adding on one slowly, step by step. So the minimum voltage we get that the capacitor is going to discharge down to is 28.099 volts peak. Our VDC is the average of our max and our min. So 41.033 plus our 28.699, divide that by 2. The DC equivalent of the circuit is 34.566 volts. Then we need to find how much ripple we have. So in peak to peak, it's going to be equal to our V max minus V min, because that's just the delta change between these two. How much total is there? So we have 41.033 minus our 28.699. V ripple is equal to 12.934 volts peak to peak. And the percent ripple, we take our V ripple, divide that by 2 root 3. We divide that by our VDC. Take the whole quantity, multiply it by 100. So our percent ripple comes out to be 12.934 divided by 2 root 3 divided by 34.566 volts times 100. Our percent ripple comes out to be 10.802%. So they're pretty quick once you understand that that's all we're doing is we're just charging and discharging a capacitor, and the output is being taken essentially across that capacitor's voltage. So whatever it charges up to is going to be the max. Whatever it discharges down to is the minimum. The average of those 2 points is our DC load line, or DC output, and then the distance, the total distance in between those 2 points, max and min, is our ripple. We convert the ripple from peak to peak into RMS, divide that by our voltage DC, so we're comparing again straight apples to apples, and then multiply it by 100 to turn it into percent. So now that we have those, let's go ahead and enter these values into our chart. So we'll come back over here if it loads, and we'll plug those values in. So we have 34.566 volts DC. We have our ripple of 12.934, and that's in volts peak to peak. and the percent ripple is 10.802%. So again, between the two, the full wave, half wave, we see a huge difference as far as what our ripple percentage is, and we want that ripple to be as low as possible. So the full and the bridge, they're both full wave rectifiers. The bridge just does it a little bit differently. It gives us a larger output to use. But sometimes there's cases where we want this one. Maybe, if we're designing a power supply that we only want it to produce, let's say 15 volts instead of 30 volts, for example. So if we take that, we could just use a full wave because we don't need that extra voltage. Because whatever voltage we don't use, which is what we're going to talk about in the next section with our pi filters, that voltage has to go somewhere. So we have another resistor, we call it a shunt resistor, that we shove everything we don't want onto. And the more power or the more voltage we shove over there, the more power it's going to have. The more power it has, the more heat it's going to produce. And the more heat it produces, the bigger the resistor has to be to handle it. When we build these guys, it's not unusual to have to see 20, 25 watt resistors for your shunt resistor because there's so much voltage being dropped. And so again, that comes into your designs. Do you want to have a big old honking heat sink with a resistor on there, or do you want something that's smaller and fits in a little bit nicer, looks better, stays cooler? So when you're designing these, you have to kind of take those into account. So the half wave, you're going to get, you can have pretty much the same voltage as a bridge does, but you're going to get quite a lot more ripple out of it. Then when you go into the full wave, you're going to have, half as much voltage out as you get, but you're going to have half as much ripple, which is better. And then the bridge, you have a larger range that you can use to get your voltage supply what you need it to be, as with the same thing as having a low ripple value. So, like I said, it just kind of depends on what you're designing as far as which type you're going to use. Generally, I think what I use is I mostly use the bridge rectifiers unless I need a smaller voltage, and then I switch over to a full wave. Very rarely do I ever use a half wave just because of how much noise actually gets into this line. And so noise, you got to think, is any kind of unwanted signal that is now into your circuit. And especially when you start getting into RF, you're going to have enough noise as it is. You're going to have a piece of wire sticking up as your antenna, and it's just going to, attract everything around it. So you're going to see so much noise coming in from that. Why add more noise with your power from your power supply? But either way, like I said, this is, just kind of the understanding the basics. The other things you just kind of keep in mind as you're going through these and designing. You're like, well, why is this? How can I change things? And that's the biggest thing too, is this is not the only way to look at these circuits. This is just an example of, the basics of what you can do. Well, you can start going through and be like, okay, well, I want my DC to be a little bit higher. So what I need to do is I need to increase what my minimum voltage is. So it comes up closer to what my maximum is. So the average goes up. So if you do that, because it's kind of hard to increase the maximum voltage when you're just plugged into the wall, you can't go to the power station and crank up your voltage so you're getting 145 volts instead of the 120 volts coming in. So we have to find these different workarounds, and there are limits to what we can do. There's, with these, obviously we have the 42 volts coming in, so that's kind of our max minus any kind of diode drop as it gets rectified. But the other way we can do that too is we could use a different transformer. So now we can take the 120 volts in, and let's say for some reason we wanted to build a 500 volt DC power supply. Why you would ever need 500 volts DC, I don't know. You're trying to power some big motor, something like that. Well, what you could do is you could take out your transformer. So now you could have, say a 1 to 4 transformer, instead of a 4 to 1. So what you do there is now you're stepping up the voltage 4 times. So instead of getting 42 volts out where you have 169 in, you could have 169 in and you could get, almost 600 out. So it's really easy to kind of adjust these. And one of the things too to think about is that's how a taser works, is it steps up the voltage several hundred thousands of times. They run off of 9-volt batteries. That's what's crazy is that these tasers, you can get ones that run off of 9-volt batteries, and then they go inside, they convert the signal to an AC signal, and they jack it up until you're putting up 100,000 volts out of this taser and then shocking the crap out of people. Um, and so, and that's just all we're doing is we're just turning the transformer over. We need a higher output. But remember, with our transformers, if we increase the voltage, we decrease the current. So with that, if we have 100,000 volts coming out of the end of our taser, we don't have a lot of current, which is good because if you had a lot of current, you could kill somebody with that. And as you guys have seen or maybe even experienced, if you get tased, you don't die. Your muscles lock up, but you don't die, and it's because it's the current that'll actually kill you, not the voltages. So anyway, so enough on that little side tangent, but just kind of so you have an idea, these power supplies are very, very versatile depending on um, what output we want, and that's kind of what the fun part is on the last part of the semester with your labs, is figuring out what output do I want? So then I know that. Then based on that, what type of power supply do I need to build? And can I get away with filtered? Does it need to be super filtered like the Pi filter, or things like that? But anyway, so the next video, like I said, we're going to cover the full wave, the half wave, all those guys. We're going to cover them again just using the Pi filter, and all it does is just adds another filtering step to get that ripple. That's what we're trying to filter out, is we're trying to filter out as much AC as possible so the DC signal we have that comes out is right on. A lot of times, you could look at, like I said, your power supplies for your computers, laptops, chargers, whatever, that has a little box that you plug into the wall. You could measure that output and you can actually see, okay, it says here that my output is supposed to be 15 volts. And sometimes they'll give them a rating. Sometimes they're just listed on the data sheets. You can go through and find them and be like, okay, how good is this power supply? And then you're like, okay, what can I build? And like I said, last year I had a student who their power supply burnt up and they were waiting for a new one and they needed their laptop. So they built a power supply. They used a filtered one and created it and calculated what they needed and had a very little ripple and a right voltage and plugged it in. Their computer booted up and charged, and they were able to keep going for the rest of the semester. And just using the knowledge that you guys learned first semester. So there's workarounds for everything. And like I said, the next section we have a little bit more versatility. We have a few more knobs that we can use to adjust and play with things and kind of go from there. But anyway, that is filtered power supplies in a nutshell. The next video, like I said, is going to be our Pi filtered, and then we'll start getting into the design. Hopefully you guys are having a good week, and remember to stay safe.